So in question 1, what I'm really asking you is, does the function multiplication by 3, so f of x equals 3x, is that function an... All right, so you said yes, that f of x equals 3x, phi of x equals 3x, sorry, is a isomorphism from Z5 to itself. So what does the Hunter zeros diagram look like for this?
0 goes to 0.
0 goes to 0.
1 goes to 2.
1 goes to
3.
2
goes to 1.
Okay.
3 goes to 4. 4 goes to 2.
Great. Of course, having a Hunters and arrows diagram, like having a Cayley table for a group, is not something we're always going to expect to have. But when we can have one, it really helps make things easier. 2 goes to 1. 3 goes to 4. And 4 goes to 2. So here's our function phi. This is the tripling function, if you like. It just multiplies everything by 3. And all the arithmetic happens mod 5. Okay, so it's definitely a bijection, according to this diagram. How do we know that it satisfies the homomorphism property? What does the homomorphism property look like?
The product rule?
Yeah.
Product rule. So that says, in general, phi of A dot B needs to equal phi of A, circle phi of B. And we're being cagey about the operations here because they can be different operations in different groups if G and H are different. But here, G and H are both the group Z5. What is the operation in Z5 by assumption? It's addition. Addition mod 5, right? And so in both cases, the operation that we want here is a plus. So what does this end up looking like? Our burden of proof is to show phi of A plus B is equal to phi of A plus phi of B.
If you apply phi, it's going to be 3 times A plus B equals 3A plus 3B.
Yes.
Which if you distribute the 3A plus B, or the 3 to the A plus B, you get...
Yeah, and how do we know that we can distribute that 3 across the A plus B on the left?
Because we know that 3A plus B is multiplication.
This is multiplication of integers, distributing across addition of integers. And because multiplication and addition of integers have that property, this equation is definitely true when A and B are integers. And it remains true when we reduce to remainders mod 5. Right? So this all works out. So it has the homomorphism property. Therefore, this is an isomorphism of Z5 to itself. Which, by the way, is an interesting isomorphism from Z5 to itself. Because what's a simpler isomorphism from Z5 to itself? Phi of x equals x. So if I were to draw the Hunters and arrows diagram for that one, it would just look like this. So here's a different function from a group to itself. I'm going to call this one e of x equals x. That is always a bijection. We can show that it also satisfies the homomorphism property. Right? Why is it true that e of a times b is equal to e of a circle e of b? For the function e of x is equal to x. Well, what would this left-hand side be? If e of x is x, then what is e of a times b? A times b. And on the right-hand side, what's e of a? A. What's e of b? B. But then how do we resolve the fact that now it looks like I have a different operation on the two sides of this equation? You go to the groups and figure out what the operation is. And if this is the identity function, what are we saying about these two groups? These groups must have been equal in the first place, right? In which case the operation would have to be the same in both cases. So all of this is just a way to show that this function, e of x equals x, always satisfies the homomorphism property from a group to itself. So always an isomorphism. We call this function the identity function. Yes. What that does immediately for us, it tells us every group is isomorphic to itself. Therefore, in this table, we can use the identity function to check off everything on the diagonal. Z2 is isomorphic to itself, Z6 is isomorphic to itself, U6 is isomorphic to itself, U7, U9. One of the interesting things we're going to talk more about on Wednesday is that the identity function is not, in general, the only function that shows that a group is isomorphic to itself. There may be others. Any isomorphism from a group to itself is called an automorphism, for obvious reasons. And so there may be other automorphisms from a group to itself, but the identity function is always one of them. And so every group is isomorphic to itself. We can check off everything down that table. All right. So give me another example of a pair of groups in here that is isomorphic. Now that we've ruled out the low-hanging fruit of everything isomorphic to itself, what else? Great. So there's an example. Z2 and U6, it turns out, are isomorphic. But since on the surface, there's a difference between those two groups, right? The elements of Z2 are 0 and 1, right? The elements of U6 are 1 and 5. So they have different names. But how do we know that they behave in the same way? Right? How do we know that the structure, the underlying structure of those groups are the same? Did you come up with an isomorphism, an explicit isomorphism for these two groups?
The order of each
All right, so we know that the orders of those elements are going to be the same. Let's put up a diagram here. So 0 and 1, those are my elements in Z mod 2. And then 1 and 5, those are my elements in U6. Well, in Z2, what's the order of 0? 1, because it's the identity. What's the order of 1? The order of 1 is... The orders of the elements are respectively 1 and 2. In U6, what's the order of 1?
It's 1.
1, it's the identity. And what's the order of 5?
It's 2.
2, because 5 times 5, 5 squared, is 25, which is 1 mod 6. So we get back to the identity. So the orders of the elements match up. But that may not be sufficient. It's a necessary condition for isomorphism, but it may not be enough. Can we come up with an explicit isomorphism? We can, right? Well, we know that the elements of order 1, which are always unique because they're the identities, they have to be associated. So then the only other option is we have to be able to send 1 to 5. Can anyone come up with, so this is we would have to show that this satisfies the homomorphism property, right? Every pair of elements we could choose over here, if we add them first and then cross over, we should get the same result as if we cross over first and then multiply. So that would give me 4 things to check, right? 4 different pairs. 0 plus 1 is 1, which we're sending to 5. 1 times 5 is 5, so that ends up at 5 also. So there's an example. But I want to be more efficient about this. Can we think of a formula for this function? No, I want a formula for phi, the function which sends 0 to 1 and sends 1 to 5, mod 2 and mod 6 respectively. I think I saw, so check that out. 5 to the x. That definitely sends 0 to 1, right? And it sends 1 to 5. Right? 5 to the x. And why is 5 to the x have the homomorphism property? This is why I recommended people do question 2 first.
Yeah, because
Because it's an exponent, and addition in the exponents becomes multiplication of the powers. 5 to the x plus y is equal to 5 to the x times 5 to the y. So this property of exponents that you learn in 8th grade, 9th grade, I don't know, sometime in middle or high school, that property of exponents is really just a statement about an isomorphism in disguise, right? Or better yet, a statement about a homomorphism property in disguise. And that's what makes this, in fact, an isomorphism between these two groups, 5 to the x mod 6. It's a bijection, as we can verify with hunters and arrows, and it also has the homomorphism property. All right, so we know that Z2 is isomorphic to U6. Meg's question is, does that mean that U6 is isomorphic to Z2? Can I turn these arrows around? We should be able to. What function would do this? Well, we would probably call it, instead of phi, we would call it the inverse of phi? Not the root. If I'm trying to solve for this x, log. Logs. It's big, it's heavy, it's wood. If anybody gets that reference anymore.
Yes, Ren and Stimpy.
Exactly. Phi of x equals the log base 5 of x. Sure enough, the log base 5 of 1 is equal to 0. The log base 5 of 5 is equal to 1. Right? And so it does what we expect it to do. Why does it satisfy the homomorphism property? Log base 5 of something equals log base 5 of something, log base 5 of something. Why does it satisfy the homomorphism property? What would I have to put in here? Multiplication. X times y, because that's the operation in the domain group now. What would I have to put here? A plus. Is this true? It's a property of logarithms that you learn in 9th or 10th grade or whenever, right? Because it's exactly the same property as the one up here, just reversing the roles of exponents and logs. So yes, this function satisfies the homomorphism property as well. It's a bijection between these two groups' elements, and therefore, we have a homomorphism going this way also. All right, so somebody tell me if that generalizes, because this, Meg, was your question. Do we automatically know, even without having to find a formula, can we automatically say if this is isomorphic to that, then that is isomorphic to this?
I want to.
I want to also. What would we have to prove in order to verify that? We know that the inverse function of any bijection always exists and is a bijection. That's general set theory. That's Math 180 stuff, right? So the only question is, will the inverse function have the homomorphism property? And that's something that requires a little bit of a proof. I posted some videos this morning, and in one of those videos, you'll see the proof of that. So all of which is to say that yes, that homomorphism of set of groups is a symmetric relation. If G is isomorphic to H, then H is isomorphic to G, which cuts in half the amount of work we have to do to fill in this table. Because as soon as I know a check mark on one side of this diagonal, I automatically get the corresponding one on the other side. So there's a couple of the more subtle examples, right? Give me a couple more examples of groups that are not isomorphic on this chart. U7 and U9. How do we know that those groups, if that's not, then this is not, how do we know that those are not isomorphic? Yeah, so we'll table the discussion of U7 and U9 for a minute. But U6 and Z6, we can definitely put an X. Not isomorphic. Why? How am I so sure, even without doing any work?
They don't have the same number of elements.
They don't have the same number of elements. And we know that two isomorphic groups have to have the same order.
If they're finite.
If they're finite. Or if they're infinite, right? Because an infinite group can't be isomorphic to a finite group. The orders of the groups are unequal. Because what's the order of Z6?
Awesome. Z6 is 6.
And the order of U6
2, 3.
is 2. Yeah. So the orders of those groups are not the same. Therefore, they're not equal. Therefore, the groups are not isomorphic. Can you give me a few more X's running on that same principle?
Yeah, U7 and U9 are both not isomorphic to Z6.
Are both not isomorphic to Z6.
Sorry. Yeah. No,
Okay.
Sorry. No, U6 I meant to say.
I think, oh no, you're right, U6. Right. So no and no, because the orders of the groups are unequal. What about Z2? Is Z2 isomorphic to anything else in this row?
No.
No. Its order is 2, and the orders of the rest of those groups are not 2. So that's quick. What's the order of U7 as a group? 6. What's the order of U9 as a group? 6.
Can you erase the ones that I said that are wrong?
The ones over here? Well, we don't know that they're wrong yet. I don't know that they're wrong yet. But maybe what I'll do instead of erasing them is I'll put them in as like a different, a slightly different color.
Oh, sure.
Just a tentative X. They may yet be true, right? But the orders of the groups are not enough to rule them out, right? What are some other ways that we can rule out or rule in the isomorphism between two groups? A couple suggestions, and then I'll release each of the 4 wins today. The orders of elements in those groups. So can we get any mileage out of that to decide whether we can fill in these 2 and those 2? So that's what I'll leave for you to talk about with your small group between now and Wednesday.